So, good afternoon, everybody. And yeah, thank you very much for the opportunity to say this few words here and to tell you how I come to, in the early stages of my career, I came to cross with path with Alan. Although, of course, this is not that difficult if you consider that Alan field of interest has gone from the very deep inside of the sun to the up to the outer corona. Well, it's not unlikely, I would say, that you get something in common or something that has to do with his field of interest. So here you see the image that Klaus was showing you before, and you can see here effectively the polar corona hole, especially the north one with the plumes stemming out of it. Now, of course, the plumes, we are now know much more about them thanks to Klaus, and so I don't have to tell you too much. But of course, plumes are the most prominent aspect in a polar corona hole. So for a long time there has been the question whether they do contribute or not to the fast solar wind. We know that the fast solar wind is coming out from corona holes. This is known from very early works in the 70s when they were comparing X-ray radiances from different regions across the sun while the sun rotates with in situ measurement from different spacecraft like Pioneer, for example, and found this anti-correlation between the radiance and the speed of the particles. And then this has been substantially confirmed by the Ulysses mission in its flights around the sun by the Zwigs and SWAPS instruments. So we do know that the solar wind comes from the sun, from the polar corona holes, but the question remains whether plumes play a role in it. Now, there has been a different attempt in the past to look in different ways whether plumes could play a role or not. One has been to look at abundances. We know that the fast solar wind doesn't show a FIP effect, a substantial FIP effect. So the idea would if the plumes they have a high FIP effect or an overabundance of elements with low first ionization potential, then you could exclude them. And that's in the first analysis came, I think there was a paper from Whiting and Feldman in the early 90s that were showing a very strong FIP effect in plumes. It seems to exclude that. But successively, other works have reduced the difference until there has been work even claiming there is no difference between plumes and interplumes in terms of abundance. So the thing remains open and probably cannot be easily sorted out using this method. Other indirect evidence favoring interplumes has been the fact that lines, spectral lines, appear to be broader in interplumes, and that could be a signature of that more energy is deposited into interplumes. Although one can take other considerations that interplumes are less dense, and you can have other reasons why the lines are broader. And I don't go here because of lack of time. The most strong evidence towards the strongest evidence, towards interplumes harboring larger flows comes from direct measurement of Doppler shift that has been done on the disk. Here you see an image from a paper from Klaus, where you do see that the neonate comes with larger velocities from the darker areas. Of course, when you look on the disk, you look at the very low down in the corona, where you have the highest densities. And so you can always argue that this is not necessarily reflect higher up, although there is no obvious reason why it shouldn't. And as well, a few line of sight observation over the limb shows the same effect, the interplume being faster. Doppler shift measurement have the advantage that they are model independent. This is just a measurement, although you still have the problem of the contamination along the line of sight. But at least you don't have to make assumption on the plasma composition, things like this. There is as well a way to measure the outflow speed when you look at plasma that is moving along the plano sky, and so you look at the plasma moving at 90 degree respect to the observer. This is through the so-called Doppler dimming. It's basically based on the fact, very briefly, that in the corona you have two effects that generates the line radiances. You have collisional excitation that is basically dependent on the square of the electron density, and you have radiation. radiation excitation from the radiation coming from the disk. We have heard that this was the way in which actually the corona emits in Lyman alpha that has been defining from Alan. And the problem when you do this with only one line, like Lyman alpha, is that you have to know as well many other parameters of that forms the lines, like but when you look at the ratio of lines, like for example in the case of oxygen 6 doublet, you can cross out the elemental abundance, for example. The temperature doesn't play a major role, and the dependence is basically depending on the electron density and as well on the local velocity distribution of the ions that is described by their temperature in the direction parallel and perpendicular to the magnetic field lines. So in practice, if you know the electron density, and if you know as well the radiance distribution on the disk that illuminates your ions in the corona, what you can do, you can calculate how much would be the ratio for the different lines. And here you see a calculation in this panel here. Okay. Oh, in that panel there, you see the calculation for the 2 oxygen 6 lines. And you see that immediately, as soon as you add velocity, the intensity of the oxygen 6 1032 drops, while for the 1037 line, it does the same, but then the shift brings at the same wavelength of the line other 2 lines that are present in the chromospheric spectrum that are 2 to carbon 2. And then when you consider the combined effect, you see that you have a modulation of the ratio that depends on the outflow speed. So basically what's happened is that, so as I said, if you have the density profile and you know the disk radiance, you can compute, you do observe the ratio. Here you see the measurement from that we did in 2003, and this is the result of the measurement in the paper from Alan from the same year. And you measure the ratio, and then you have to explain this ratio, so you make a model, and if you are in excess of this ratio here, you add the speed outflow until you take down to the ratio that you do observe. Now, the ratio in plumes, it's an interplumes, it's not too different, although here there is a larger separation between the two, but we do also observe plumes having a lower ratio in interplumes. Now, when you translate, the point was that when you translate this into outflow speed velocity, what we found was that the velocity profile in interplume was not that different. I am talking here mostly about the lower part, that is the ones covered by Sumer, that I should say, because that's the first group of data, and then those ones are from UVCS, and there the agreement we are in agreement in the subsequent works that Lucia Abbo will show later. She will describe this more in more detail. But the problem came from the plumes, because in our work we could explain, we could assume a semi-static plume or with very negligible velocity. But in the case of the work of Alan and his co-worker, they found a plume that is going much faster than an interplume. So the discussion started, and was one of the topics we brought as well at the EC workshop. With a very nice and intensive discussion about this argument, a discussion that has not completely finished. And it's here you can see an image from what you can call a special session at the EC workshop. And those discussions have been always very nice, and at least for me personally very full of inspiration, and I have learned a lot from them. So what can I say in terms of final notes forward is that the discussion is still open. We should always remember that we are talking about 2 measurements only, 1 measurement that we are comparing. And so that definitively there will be necessary much more measurements should be taken and should be analyzed before to come to a conclusion. Those measurements takes an incredible amount of time to be completed. Any temporal effect, especially in plumes, would be completely smeared out into the data and may play a different effect in different data sets. So what we hope is that the next generation of spectrometer, now we have SPICE surely flying on solar orbiter, and maybe the spectrometer that is being proposed for the Solar Sea mission maybe would come into light one day, hopefully. And those instruments should, what we hope, they should provide ideally all, but at least some of those improvement respect to the instrumentation that is now basically, we can almost call past instrumentation, although still operational. And this is a larger throughput to increase our time resolution, and especially a simultaneous measurement of the electron density that is such a key measurement in this type of determination and in Doppler dimming analysis, as it should always be measured simultaneously with the data you are going to consider. While this is very rarely the case, I would say it's almost never the case. And there's a better stride subtraction, another critical effect, and that's hopefully more and more discussions to come in the future. Thank you.